it. So the talk will be on reachability in subclasses under the patronets, but it's the first failed talk, so let me give the story. Around 2.5 years ago, I recruited 3 master students almost at the same time. And for this first student, I told him, I have a problem, I thought a bit about it, I think it's going to be difficult, so I cannot promise anything. And he got a Dix paper. And then I said the same thing to the second student, and he got an ICAT paper. And the third one, I told him, I didn't really think about it, but I think it's going to be simple. And we've never published. If I was a student, I don't think I would like to have my name here. I just joint fail with someone else. But at some point during his master, I thought, okay, I know someone smarter than me, so I will get him on board. So I asked, so I think out of courtesy, I should share that.
Michael, just could you move a bit closer to the screen so that we can record it?
I think I should share the failure. So before I tell you about our failure, let me tell you something else. First, you may wonder where the hell is Sherbrooke. It seems to be in France, but it's not in France, it's in Canada. So my first challenge was to get from Montreal to Warsaw. So this is Charles de Gaulle in Paris, this is Munich, this is Vienna, Warsaw, Helsinki, and Canada has very weird codes for their airports, so the Yule is actually Montreal. So that's me, and I had to come here. And when I travel, I try to not speak English at every airport. I try to mumble a few words. And I thought, okay, if I would fly directly to France, then I would just keep the same language, and that blue thing on my head is supposed to represent French. And then, if I travel to Munich, I'll try to switch it to the 10 German words I know. So there's a graph of a few airports in Europe and Canada with the semantics. So for example, if I were to fly, sorry, I should speak. If I were to fly to Paris, I will keep French, but then switch to the 3 words I know in Polish. So the red is Polish. Another way, I could have gone to Munich, switch to German, then directly go to Warsaw in Polish. Or I could have gone to Finland, and I know 0 word in Finnish, so I didn't travel there, but I could have switched. And if you follow the semantics, and it doesn't really correspond to what you would imagine, because it just says I should change language. I could have switched to Polish in Munich, probably a bad idea. And then I could have taken Finnish here, and then go back to Polish in Warsaw. Okay. So actually, I booked this flight. There's no direct flight from Montreal. And when I arrived in Munich, they told me I missed my connection, and I should do this. And after staying 2 hours in a line, I convinced them to go through there. And I told them I'd rather go there because the connection is longer, and at least I'll speak French there. And then I changed my slide to this. I probably should have booked this because it took me 24 hours of transport to get.
How much CO2?
So
How much CO2?
Oh, this I don't know, but I'm done for the year, I think. I should have booked this, I think. So this toy example is another data patronet. So we've seen this model twice quickly yesterday by Sławek and Piotrek. So you have these places that contains color tokens, and there are variables on the transitions. So I prepared a slide, so I may as well define it in a bit more detail. So you have a finite set of places, it's a patronet instead of a bus. You have the transitions, which is finite set T. And the arcs are labeled by weighted variables over n. And I will use the same semantics as Piotrek. So when I assign color to the variables, I assume that each variable gets a distinct color. So I cannot put blue on Z and blue on X, for example. So a marking is just an assignment of colored tokens to places, and there shouldn't be infinitely many tokens in the place, but at any time, but the color domain here is infinite. Okay. And I suppose that we can only compare for equality or disequality. So for example, in this patronet, if I assign, I'll call the colors by the shapes in case some people are colorblind. So if you assign circle to X, box to Y, and triangle to Z, then you could consume these 2 tokens, this one, take this one, and produce 2 triangles. But then you're stuck, okay, because the only way to fire this would be to take 2 circles and 1 square, but you cannot take the circle area in X, so it's a deadlock. So the kind of questions I'm interested in is reachability questions. So given such an ordered data Petri net, which I'll just call UDPN, starting first from such a colored marking, can I reach another colored marking? For example, can I bring another circle token here without moving anything? Well, I can move things, but at the end I want this. So formally, the reachability problem is as you would expect. You're given a net, 2 markings, and you want to know, can I go from the initial marking to the target marking? And if you have no colors, then this is well known in this room. It's Ackermann complete. It was proven by several. I think everyone is here in this list. But if you have colors, the decency is open. That's what I mentioned. Although it almost freaked me out by saying he almost solved it. But it seems to still be open. If you're allowed to have special transitions, which are called new transitions, where you can create fresh colors that have never happened in the history of the computation, then this is undecidable. It's also undecidable if you have order on the colors. And a related problem is the coverability problem. So the same input, but you want to reach something that covers your target marking. If you're not familiar with cover in this context, you want to have higher number of tokens or equal, but you also want the colors to match almost. So for example, you have 2 circles for 1 square for 1 square, 1 square for 1 square, and you have more colors, or you're allowed to rename the color. If you're colorblind, this slide is ideal because you won't even see the difference. So for coverability, the problem is decidable in hyper-Ackermannian time. It was shown a while ago, but there's more recent work on coverability trees, so there's a way to decide this. So UDPNs are one of the few extensions of Petri-nets where reachability could be decidable. And I think for a master's thesis, it's too ambitious to establish decidability. But I asked the student, well, is there a subclass where reachability is decidable? And if so, what is the complexity? Okay. So I told him, let's try like outrageously simple subclasses, and maybe we'll show it's in P or something. So the first class I proposed was S-nets. So the place nets, I think the S historically comes from Stellen in German, which means place nets. And the definition is as follows. Each transition has exactly 1 arc as an input and 1 arc as an output, and that's in the context of colorless Petri nets. And for S-nets, well, first of all, remark that the number of tokens never changes, so they're quite simple. Every time you fire a transition, you must move a token and keep it in the Petri net. So in particular, they are bounded, so definitely reachability is decidable, but reachability is much simpler. One can show that if you can start in marking M with no colors and reach M prime with no colors, then you can do it over the so-called marking equation over the rings. So one way to phrase it is when you fire transition, you're allowed to go below 0, and on top of it, you're even allowed to break the tokens in half or in parts. And this continuous version is much simpler. It can be solved in polynomial time through, for example, linear programming. So since we have this equivalence, although it's a bit of an overkill, that's one way to argue that the reachability in S-nets is solvable in polynomial time. So there's hope that the reachability with colors is decidable for such a simple class. And one such example is the one from the very first slide. This is an S-net because each flight just connects one city to one city by possibly changing the color, which were languages. For example, from Montreal to France, you need to keep the same language. Does not need to be French. If you start with English, you need to talk in English in Paris. But that models the first step. Okay. And it's quite easy to show that if you have an initial marking with colors and a target marking with colors, and there's only 1 variable in the input arc and 1 variable in the output arc, you never need more than 2 extra colors. So maybe you have red, blue, and green in the initial marking, and you have yellow and orange in the target marking. If there's a way to go from M to M prime, there's a way to do so by using these colors and possibly 2 other colors that are not in the initial and target marking. Such an example would be as follows. If you want to go from blue to red in Warsaw, you just need 1 auxiliary color. You could do the city thing I told you. You could do French, Polish, Finnish, and then Polish. Okay, so blue, light blue, red, dark blue, and then red. And then the only extra color is this dark blue. But if some weird reason you want to start in French here, so light blue and end up in light blue Warsaw, you need two auxiliary colors. Okay, so you would do blue. Then you cannot, if you put, let's say, orange. And then if you put blue right away, then there's no way you'll end up in blue. So you need to put, I don't know, pink and then blue. So you need to make two switches with two colors that didn't exist to reach a target. But you never need more than this. And because of this, you can take your net, copy paste it 2 times plus the number of colors in the initial target marking, and you get a colorless net. And if you take an S net and you copy paste it, it remains in the class. Okay, you'll send one token from one copy to another copy, but you maintain the property that there's one arc in each transition. That means that the problem is in P. So I thought, great, let's move on. This shows that this project will lead somewhere. And then I moved to T-nets. Okay. So T-nets is the opposite. Each place has exactly one input arc and one output arc, but transitions don't have this constraint. So it's not true in T-nets that the number of tokens never changes. For example, if you fire this transition, you'll get 2 tokens. So you increase the number of tokens by 1. But it's true that the number of tokens in a cycle never changes. So for example, there's 2 simple cycles, one that goes through here and the other one that goes up through the bottom. If you fire this, you have 2 tokens, but in both cycles you still have 1 locally. So in this case, this net is also bounded. And it's kind of, well, I don't know if it's well known, but it's known, and it's even some exercise in this course in Unix, that if you want to start from an initial marking M and go to M prime, it's true if and only if the same thing as for S nets, so you're allowed to break the tokens, you're allowed to drop below 0, but you need something else. You need to make sure that if you have a cycle which is unmarked, that you don't use any transition. Okay, if you have a cycle with no tokens in them, there's no way you'll ever be able to fire transition because it will be a siphon that is stuck. So you just need to add this extra condition. And again, you can use linear programming here. So that means that's in polynomial time. So I thought it's simple without colors. It's probably simple with colors. So first of all, see that this continuous approximation doesn't work for colors. So if I start with one circle and I fire a transition, I will get, for example, square and triangle. And then I'm stuck because this transition needs to come colors and there's no way to generate more. But what if I could split the tokens to mimic the theorem? Then I could fire this by 1/2, and so I keep 1/2 circle and I generate 1/2 square and 1/2 triangle. And then I fire it again, but I switch the colors of Y and Z. So this way I get half of both. I get a mixture of both colors. And then I can fire this transition by 1/2 by taking the triangles, and I generate half a circle, and then I generate half a circle, which makes a full circle. But there's no way we could reach this in the discrete case. Okay, so it's not an if and only if. So we cannot resort to this machinery. And then we were wondering, well, maybe it's harder. Okay, so the problem is indeed harder in the colorless case. So reachability on order data T-nets is NP-hard, and you can reduce from 1 to 3 set. So in this problem, you're giving it 3 CNF formula. You want to find a satisfying assignment, but on top of it, you want exactly one of the 3 literals in each clause to be true, and the 2 others to be false. And there's a neat gadget, which is quite simple. This part in gray is like just a dummy transition to make it a T-net. So you take W and you bring back W and shoot W, but this is totally dead, so you can never fire it. So actually the net I have in mind is this one, but it is a T-net because I can artificially put this. And then there is one side for it, there's one such gadget for each clause, and there's one column for each variable, and it works as follows. There's a dark token at the top, and there's n red colors for false. There's the 1 false, 2 false, 3 false, and so on. but there's only one version of true, which is square. So for this variable, I can fire this transition. I need to put square or 1, and there 1 or square. So this variable must be true or false. And it will consume the black token. So for example, I could bring false here, and this represents the fact that I'm assigning false to x1. Then if I fire this one, let's say I bring 2, if a variable appears in several clauses, we bring the dual of the letter. So if I bring y here, I will bring x here. So it will complement the Boolean value. And I could do this for all variables. And then this is my assignment, and I want to check that I have exactly one true value per clause. And how we do it, we put all the false value here, and it only works if we have one true value in one of the 3 literals. So I could empty everything. So the question is, from the initial marking, can I reach this one? Where these places have never moved, but the black tokens have vanished from the net. Okay, so this shows that it's NP hard. So still, we were wondering, well, is it decidable? That was the motivation to show that some simple subclass is decidable. And the only thing we could prove is this. So if it's strongly connected, so you look at the picture as a graph and everything is connected. Then it's in P space, and if on the opposite there's no cycle at all, then it's in P time. So both are quite simple to argue. So if it's strongly connected, as I've mentioned before, in a T-net, the number of tokens in a cycle never changes, and colors don't change. So for each place, if you go from the initial marking to somewhere, the number of tokens in a place P is upper bounded by the number of initial tokens. So if you're very crude, you can see that in any reachable marking, there's never more than number of place times number of initial tokens. So it's bounded. However, the reachability set is not necessarily bounded because you could have a lot of color renaming. But up to permutation, it's fine. Okay? Due to this very simple observation, which has nothing to do with T-nets, it's a general simple lemma. If you go from the initial marking to somewhere, and you go to the same marking up to a color renaming, so row here, just rename the color, and then you go to the target, you may as well go from M init to M, and then rename the firing sequence W with the other color. So if blue is becoming yellow, then yellow becomes blue, and back and forth. And then you'll reach the target up to this color renaming. And if the color renaming was not touching the target colors, then that means you're still going to the target. Okay. So that's one crude way to upper bound it. If you look at the maximum number of tokens plus the number of color in the target, and you look at all the ways to partition these tokens, this will give you all the possible colored markings up to renaming. So that means you can just guess or run non-deterministically in the net and show that's in NP space, because it's exponential but not too large. So you can guess it on the fly. Of course, since NP space is equal to P space, that shows that it's in P space.
Sorry, why did you use strongly connected?
Where did I use it? Because each cycle preserves a number of tokens, and each place is in a cycle. So there's no way to shoot new tokens, or less importantly, to get rid of tokens. Other question? So for the acyclic case, so now you have a pitchnet, and there's no cycle at all in its structure. Then, actually, in any acyclic UDPN, you can go from M to M prime if and only if you could go with the Z-VAS semantics. So you're allowed to temporarily drop below 0 as long as you come back. And that's because if you guess a solution to, not guess, but if you have a solution with the Z-VAS semantics, since it's acyclic, you can fire it in topological order. And then you'll get a valid run with N-VAS semantics. So, and this is known to be in NP. Okay, it's been shown at LIX 2017. It's well known for Z-VAS without colors, but this is a picture with unordered data. So actually it was shown by Piotrek, Jérôme, and Patrick Totzke, which I think no, he's not here, that testing this amounts to testing a few membership queries in subgroups of ZP with addition. And the more technical details are here. If you look at the difference of M prime with M, which is like a matrix. So it's not a marking because some values could be negative, but it's like a pseudo marking. You can go from m to m prime if and only if the first bullet point is easy. If you forget about colors and you forget about variables, there should be a way to go from the initial marking to the target marking. Otherwise, there's no hope to achieve it with colors. And the second part deals with the color. If you partition your net in all its copies with the distinct variables, so just the x variables, just the y variable, and so on, there should be a way to generate the number of tokens in each color using the effect of each transition limited to these variables. Okay. So the important thing here is that both bullet points get rid of the colors and they ask question on the uncolored version, and then you can just reduce to integer linear programming. So, and from this, once you extract this, it's relatively easy to show that instead of having solution over Z, you can have solution over R. And this is very specific to T-nets. And internally, if you have a solution over the reals and you take the ceiling of the solution, in T-nets, it remains a solution to the system of equation. And what does it mean? It means the problem is in P-time, because it was shown by these people, in particular by Piotrek at FOSAC 2019, that continuous reachability in R-north-direct data pitch nets is in P-time. In acyclic T-nets, you can reduce to this. So this is what we know. But what about the general case? So this was the net from the very beginning, well, the second one. So let's say you have a circle here and you want to bring a second circle there. You can do it, but you need some extra colors because there you need to fire X and Y. So this is an example where the net is not bounded. To answer the other question, I could spit out lots of tokens here. And I could generate the opposite, and then bring the three circle, bring a square here, then bring square, square, and get rid of the circle like this. Then get these three there, then get a circle, then do this, and then get rid of the extra square. It's kind of a way to feed the net, do something, and clean the net to reach this marking. But how do you determine this algorithmically? We have no idea. Okay, but it seems so easy. There always seems to be a way. Not everything is reachable, but every time we're coming up with an example, it seems you kind of feed the net, you do something, and then you clean the surplus that you've got. And we've been stuck here. And how could we solve this? One option is we know that in a strongly connected components, it's in p-space and it's bounded, but it would be nicer if we have a characterization that you can symbolically show that it's kind of semi-linear or something. And then you could glue the net in all its parts in the back of the strongly connected components. Well, we don't know how to do this. We know that continuous reachability doesn't work, but it's not enough. It needs to be more. The other option we consider is bounding the number of auxiliary colors. And we think we don't need more than something like number of places of some number of variables colors. Like for example, in my example, I brought a square and I got rid of it at the end, but we don't know how to prove this. And that's it. So in summary, well, the reachability is open for the main problem. Some people conjecture it to be decidable, in particular Sławomir. And but we failed to establish it for a very limited case of T-nets. Of course, maybe we didn't find the right tool, and it might not be that difficult. Maybe it will be solved in 20 minutes. Well, maybe also it was not the right class. I just naively started from this because we use these classes as exercises sometimes in feature net theory. There may be other interesting classes. I think bionets, for example, may survive better because they're similar to S-nets. Maybe communication-free nets and so on. But yeah, I don't know how to do it, so.
Any questions?
A stupid question. Yes. The +2 bound the S-nets, can you use it to prove the Futurama theorem? You know,
The what?
Futurama theorem? Sorry,
Now you're going to tell us.
it's a simple theorem. It says that if you have a permutation, if people swap identities, and you have some people who are in the wrong bodies, you want to refer them back, then you will need to add 2 more people, and then you can restore everything back to normal. I think it might model the assets. We can do
But
it
they
offline.
need to switch
It's
at the
really, it's completely irrelevant to anything. So.
Other questions? Was this already solved by some without knowing? No? Okay. Well, thank you.
So we continue the topic of datanet, so maybe not Sławek, but Taylor.
Thank you. I profit from the very nice introduction of the model by Michael. Most of the job is done already. So it will be the same model, right? Fetchiness with equality data, or equality colors, if you wish. But will be like on the other end of the complexity hierarchy, not in the low complexity classes space or so. Will be inspecting classes above Ackermann. So yeah, we have this model, right? Ackermann complete, and a number of extensions of it, like PBus, or maybe DBus, maybe double S here, more right, or the model I am interested in, DBus, right? And the natural question is, can one reuse the technology, Ackermann hardness here, to any of these 3? So the history, the story I want to speak about is about an attempt to go there, a failed attempt, right? So I need to recall a bit what's the cornerstone of the Ackermann hardness. I want to recall very quickly, very imprecisely, the concept of amplifiers. Okay. The amplifiers will live in this Grzegorczyk hierarchy of fast-growing functions. So again, I need to recall it. It's pretty easy. So we start with some very basic function, say W, the first floor, right? And then each next floor is by iterating the previous one. So like I plus 1. Is it still visible in the font? I need to save my space. If you want to compute the next one, right? What you do, you invoke the previous one, argument many times, right? Starting from whatever, maybe 1 is. That's the recipe to go 1 floor up, and at the end, at omega, or actually this is the successor ordinal case, so there's the limit ordinal case. Say omega. What do you do at omega? What do you do at omega? What do you suggest? Fn of, say, n. Just 1 time, say. Some diagonal, right? Good. So Ackermann hardness here is due to Fd amplifier. The gadget for this way. D is a natural number. So whatever D, one can construct a gadget bus. Okay. What is this? What is this amplifier? It's like, in a sense, computing this function. Something which computes this function in certain, under certain conventions. So what? Under certain conventions about the input and output interface. Very briefly, imagine a bus with possibly many large dimensions, so many counters, but you distinguish 3 input counters, say B, C, and D, and those will distinguish 3 output counters, say B prime, C prime, and D prime. Okay. Maybe there are some others inside for implementing the thing. And now, to to speak about amplifiers, you need to have an idea of triples. So triples are all counter valuations, yeah, which are zero on all counters except the three ones you are interested in. And n triple would be an evaluation where b is equal n, so n triple. B is like fixed. What about C and D? Whatever, as long as there is multiplication. So as long as C equals B times, say D equals B times C. Okay, so this is n triples. Otherwise, all of our counters are zero, really 0, 0, right? And the idea here is to compute from, I mean, if you want FD amplifier, you want make n triples, yeah, into FD of n triples. What does it mean, make? Imagine I give as input all possible n triples, yeah, infinitely many of them. And I observe what's the output here. Right? At the ending instruction, I can test for 0. But just once. I can test one of these three, say D, for 0. So I input all possible n triples. I execute my gadget, test for 0, and observe the output. And the gadget is correct if what I observe here is exactly all these triples. The gadget is a kind of factor which inputs triples, which are small, outputs triples, which are big. Actually, of course, it inputs a single one and outputs a single one. But the definition concerns like joint order. Right? Is it kind of clear what the gadget could be? It's a way of computing a function by a trinity or a bus. Certain specific way of computing a function, right? It does require a zero test at the end, but only at the end and only once. It's kind of reachability computation of a function. And now we are still in bus, right? But we'll go soon here. F1 amplifier. Not a big deal. You just need 6 counters, nothing else in the middle. You can imagine a doubling, right? Just double everything. We write from D to D prime and you check that you have written everything. So it's kind of easy. Right? How to do the next floor amplifier, having the previous one? Actually, you observe that having this well-prepared input, because n triple is like a well-prepared for it. Because you see a multiplication. Having that, you can simulate a number of things. For instance, you can simulate n zero tests on a counter. So I'm looking at the definition here. What's happening? I get my input counters, input triple, which is this argument. I want to compute my output triple, which is the value, which is this. But I use inside a sub-gadget, right? I use inside a small gadget, which can make this. And I want to use it a number of times, n times, right? Starting from something which is like initializations, okay, it's obvious. And now I need to repeat n times, which will happen. We're doing n times. At every iteration, I would need to test d double prime for 0. How it's happening? It's happening due to this n triple in the very beginning, which I was given. N triple allows me to do n0 tests. Right. I don't want to go to details. I want to give you the structure of the approach here. Any questions? I could expand a bit, but I'm not sure if this is needed, right? So there is an idea of a gadget which allows us to lift to the higher floors at the price. I mean, every floor costs us 3 extra dimensions. That's the idea, okay? Which means that you can produce FD amplifier bus in dimension 3D plus 3. Altogether, this gives us F omega hardness or Ackermann hardness. Good. So now let's try with colors. Okay. So it's kind of known that if you have colors, then in dimension 3 you can simulate already bus, general bus. Okay. But that's not the way to do here. Our approach was because we need to go further. We need to go beyond the complexity of bus. So our idea was, okay, what about using colors for the floors, right? If I can produce n different colors, I have immediately like free n. I could using free counters. I could simulate free n counters, free n different counters. Yeah. So this is kind of easy, and you can really produce, given a triple, an n triple in the beginning, right here. You can produce n different colors, build the whole thing, the whole like gadget inside over sub gadget and so on, build the whole construction in fixed dimension. Okay. So in other words, you can realize not only FD amplifier, but you can realize even F omega amplifier. Okay. So simple fact, corollary of the Ackermann hardness here is that reachability in data bus is F omega hard, right? Whatever it exactly means, but not. This is the corollary. But what's more important here that sorry. One can compute an F omega amplifier as a bus. Okay, one can compute this amplifier in fixed dimension data bus. I don't know exact dimension, but it's like a small number. This is what is impossible in bus. Because what you can do in bus, you can do FD, whatever D, but you can't do F omega. Why? Because if you have F omega amplifier, you can go further. Just add 3 counters, and you have F omega plus 1, and F omega plus 2, and so on, which is impossible, right? So we are already kind of beyond bus. Good. But then we hoped for a significantly better lower bound in data bus. Okay. And me with Łukasz Kamiński, who is sitting here, it's conjecture. Reachability in data bus is, and okay, now I can put some ordinal. We hope for that. We hope that we can go really far. Namely, okay, if we have omega at fixed dimension, why not to repeat the construction? Okay, hoping that at every level we'll get to like next power of. But actually, our like huge construction failed at some point. What we can do way less than this. We can do something. So at least it's like probably harder than bus. what can be shown is that the problem is f omega squared. This we know. And this is not a big achievement, simply because once fixed dimension is enough for f omega, we use another fixed dimension to build like another omega floors on top of it. This gives us 2 omega, and so on. And in the limit, it's like omega times omega level of hardness. That's routine repetition of what we really have from mass. But I mean, the open question or the failed approach, the failed attempt, which hopefully can be improved, is to reuse this technique U with the extra resource and colors to get some really better lower bound, like omega square lower bound.
So you were somehow hoping that you have like fixed dimensional amplifier from f omega power I to f omega power I plus 1, something like that.
We hope for like every extra additional like fixed dimension added. We hope to like repeat this omega floor construct. It's like an omega floor thing. Omega actually in the implementation means whatever n given in the n triples. At some point there is some n, but as this n triple is arbitrary, this n is arbitrary, it amounts to omega floors.
So what's the problem with reaching f omega square in fixed dimension?
That's what we failed. That's exactly what we failed. Yeah? Like the first check is, can you do f omega squared in fixed dimension? This we can't. We need to use all the dimensions, like whatever n dimensions for omega squared. But yeah, it's not hopeless. Right? It's not hopeless, but it's also not obvious. What's on the whiteboard? This is obvious, including this fact. It's like obvious. Beyond that, we failed. Yeah.
How far do you expect the upper bound to be?
Okay, it's difficult. I don't have like strong conjectures, but I have a weak conjecture which says that it's this for data bus, decidability and this complexity, f omega to omega, and you can go beyond. We can consider nested equality data. It's exactly the same like, I mean, adding data is the same as adding nesting. And then nesting of nesting, like you can imagine k deep nesting of data. K tuples of data with limited equality tests, like in the nested equality tests. And I like conjecture that it's for k nested, it will be the tower of k omegas. Like it's like multiset on top of the previous model, multisetting a model. Each next level is like configurations are multisets, final multisets of configurations of the previous one. So looks like it could be like one floor up in the tower of omegas. Easy to say, I mean, but we conjecture, yeah, not a strong. Other questions? That's all what I have to say. I could go into more detail, but I'm not sure if this is really necessary here.
Okay, thank you so much.